as I get cited there. This is a talk about, this says, debugging strategies. Of course, people who are new to programming, Python in general, but programming. Let me get rid of that annoying cursor. Yeah, sorry about that. Anyway, so talked to a bunch of people, and sometimes people who are good developers don't necessarily know how to tackle certain kinds of debugging problems. And so I thought maybe we could have a discussion about that, and just a discussion because I don't know all the war stories and all the cool stuff about debugging. So I'm hoping that the audience might have a few ideas about some things they've run into. So it's not going to be about any particular tool of software, not about the debugger in depth or anything. It's more about the philosophy of debugging and how you approach certain kind of problems. And sort of the tools in your arsenal when you're debugging problems is the causes of bugs. Where do bugs come from? We're going to talk about that and how we can mitigate that. The traceback is your friend. If you may be intimidated by it when you're new to Python, we'll cover a little bit of that. It's a universal debugging tool. When something goes wrong in your code, how do you get your hands into it so that you can find out what's going on and maybe introspect it or poke around in the code while it's running? And then sort of a taxonomy of bugs, of the different kinds of bugs that you tend to run into, and maybe some ways to start resolving those bugs. So make sure that a little bit bigger. Yeah. So of course, the first thing that any Python programmer uses for debugging is the print statement. And I admit I do use that still a lot. And so you sprinkle those through your code, and you take them out when you're done. And certainly that's a tool that's in your arsenal for doing debugging. Then of course there's the Python debugger, so it gives you a little more control to go in and set breakpoints, single step through the problem areas and such. Of course the debugger, you have the things of, do you want to start the debugger as soon as you run your program? You may also simply later find that there's a piece of code that's giving you some trouble, and you'd like to drop into the debugger at that point in execution. And so that's a different way of using the debugger. And then, of course, there's the dropping into it when a problem actually occurs, as in an exception is raised and nobody's handling it. Take me in the debugger. I need to figure out what's going on here. And so those are the three ways. There's also the logging module in the Python standard library, which logging is a very, very good thing to get into the habit of doing in your code. And there's very good support for that. And unit and functional tests are good for debugging in the sense of they will alert you to problem areas in your code as soon as you've made a change. And finding a bug as soon as you've introduced it into your source code is certainly better than finding it later, because your mind is already on the problem. You know what you've changed. So having a good test suite will improve your debugging. And then if you have problems, some bugs are performance related. And the Python has a standard profiler that will tell you which parts of your code are taking up more or less time. And so you can track down where is the timing bug. And then the best, of course, is the Python prompt. It's our best debugger in the sense that you can actually go in and invoke functions, print variables, gives you the ultimate power. And of course, we're lucky in Python to have the ability to do that compared to some other languages, say. So where are bugs coming from? And of course, one of them is misunderstanding by the programmer. He may be misunderstanding the API. He didn't understand the purpose of certain arguments. Or he may have misunderstood the requirements that go into some projects and have to iterate on that. Maybe the source code got out of sync. The code was working. He changed something. And now it's the function and the caller of the function don't agree on how to pass the arguments. And so that introduces a bug that you may not find until that code is invoked. And that may be like a programmer who's harried, very, very busy, or just neglected to take care of that detail. Another one is assumptions about the environment. The programmer may have believed that he had unlimited memory. He may have believed that he didn't care about disk storage, things like that, and those assumptions may not be valid. And so he'll have to be careful about that. And then, are there any other causes of bugs that you think there may be in the Python? I was going to see if the audience had any other, that I cover the scope. What do you think bugs come from, other than those things I've listed? Anybody have any ideas? The what?
IPSIDIC.
The IPSIDIC world. Translation, yeah, errors. Yeah, that's true. Data translation errors where the data was corrupted or was it problematic. So anyway, that's sort of the big picture of that. Resource management, of course, is a major cause of bugs. We often think that programs are, the bug is caused by inputs. And certainly from an academic or theoretical point of view, the inputs to a program in the academic sense is, the cause of problems or, it illustrates the bugs in code. But programs don't occupy a vacuum. They actually exist within a computer, and they have assumptions built into their code that's not always documented or thought about. Sort of like, we're all taught how to solve the Fibonacci with recursion, but we're not always aware that when we do certain numbers, it may overflow the call stack for Python. If it's 4,000 levels, things like that. So you have to think about that when you're programming. Disk resources, so that you may be out of disk space for the data, or you may be out of directory entries, which always throws people onto the Unix platform and a few others, where the disk space has lots of space, but it's run out of inodes. It's run out of directory entries in that sense. And so you can't create more files, but there's plenty of space. Got to think about that. Files in use by other programs in the system, maybe they're locked, and you ran the program and it worked, but now it's messing up, and you're like, look, I didn't change the code. Well, no, you didn't. Something else is now running at the same time. You got to think about that for debugging. Permissions. Maybe on your own machine as a developer, you have unlimited rights. You give it to a client. Now you have a problem. You didn't think about that in your code. And then the limitations on the compute resources, such as the running out of memory, as I said, the variables, garbage collection, and also you can run out of threads. Sometimes people are surprised that Linux, for example, at one point had 4,000 threads, unless you recompile the kernel. And if you were using that for gaming or something and creating a thread for every object, every character, suddenly you've run out of space. And that's part of the reason that the stackless module was created for the gaming and all was a lightweight thread for that. But there's always a limit on the number of threads. And then excessive concurrency uses, where you basically are dividing the work among a number of threads or processes, and theoretically, sure, that sounds great, and you divide it among 10, and then you have a larger data file, and you divide it among 1,000, and then next week you divide it among 10,000, and suddenly you find that while theoretically you can divide the work, practically you can't divide the work on that single CPU machine or 4-core, 2-core machine. Suddenly, the theoretical impacts the reality. So those are just, as you have to think about that while you're debugging or thinking about the correctness of your program. And then network resources, for maybe you can actually have limits on the number of sockets. Put down there, sorry. I think there's another item at the bottom. You may run out of sockets. Sockets also are limited resource in systems, and may have problems with the DNS or network topology, where it worked great on your machine under localhost, but then you delivered it to someone and their networks were different and your program didn't handle that. And you thought it was a simple programming problem, and it's a little more complicated. And then maybe restricted lower ports, because as a developer you may have the rights to talk to the lower 1,000 ports under Unix and other platforms sometimes. And then you deliver it and it doesn't work under the lower 1,000 ports. Triggers a security issue. And then packet chunking is one for, sometimes you have packet chunking in the sense of you open a socket, you're sending some data, and your system is lightly loaded at your developer machine, and you built up the packet in pieces and it got sent. But if you tried that on a busier system that has lots of network traffic, maybe the packets are going out in more pieces, where you gave it 3 chunks and it went out in one packet on your machine, but on a busy machine the buffer was filled early, and it sent pieces out earlier, and now both ends have to handle putting things back together. And people who use raw sockets tend to run into those kind of things. Or they read the socket and get something, and they don't realize that they haven't got all the pieces yet, and they go on and operate on it, but they have to wait for the other pieces. And the twisted web framework, or twisted framework, not web, twisted framework is very good at handling those kinds of problems, easier than rolling your own solution. So you may think it's easy, and then you have to handle a lot of corner cases. And Twisted is designed to handle that kind of issue smoothly. And then changes in network I/O behavior, where it was not on your lightly loaded machine, it didn't block when you did certain I/O operations, and now when your machine is on a server so busy, you issue I/O calls, readers or writes, and they do block because there's several other programs that are running and it hasn't gotten around to you, and now your timing characteristics have changed on your system. Tracebacks. So if you've poking around tracebacks, you probably have seen some of those if you've been in Python very long. Of course, it tells you the file that it's coming from, the line number within the file, and then the method or function inside there where that frame is, and then it will show you the line of code that was there. Okay, so it will have a set of frames, the call frame, as in A calls B, calls C, calls D, and A would be at the top, and D would be at the bottom. As you said, the most recent call is last, but the idea is that you hit the file name and line numbers, and so the idea is continued on down as you're nesting your trace, and it shows the lines, and then you actually finish with the name of the exception that was raised, and then a message for the exception. In your case, we raised value error with a message, and so you print that. So that's sort of the overall traceback. The things to be aware of course, is that the actual cause of the problem may not be the last entry on the stack. I see there's a lot on mailing lists where people actually what they do is they read and they stop at the first one, because this just overwhelms them. If they stop at the first one and they say, what's wrong with my code? You're like, well, you really got to go down here and come back up. And people forget to do that, or get lost in the details, as it were. The other thing is the path names of files actually can lie to you. That you may see an exception and it puts a path name out there, and then you go look there and you don't actually have any source files at that spot. What happens is that whenever Python compiles the .py files in the .pycs, it freezes the directory path names into the PYC files. If you then move them to another system, they're wrong. I run into that where people compile things under Windows, I run into Linux, or vice versa, and I'm like, why are there Windows paths in my Linux code? Oh, well, it's not. It's just the PYC files have those cooked into them. And so that can be a misleading fact when you're trying to track something down. So tracking down when something goes wrong in your code, the -I option on the Python command, if you haven't played with that, is really, really good. Basically, it says, run my program, and when you finish executing, drop me into the Python prompt. So now you can do like a post-mortem analysis of your data. You can actually type out what it did. You can invoke some more functions. You can print out your data structures. It's really good for, after you've ran, let me get control and do that analysis. Similarly, there's the standard library has a code module. And you can call code.interact local equal locals. And what that will do is whenever that code gets executed, it will drop you into the Python prompt. And then you can exit the Python prompt, tap the exit, and it will continue running your program. So it lets you say, stop here, I'm having some trouble, I know there's something wrong with this data structure, or maybe there's something wrong, I want to poke at this tree structure, And so you drop in the prompt, check it out manually, and go, okay, it's good. And then you exit and go on with your execution. So that leverages the debugger, the Python prompt. You can also put around your piece of code or around the main program a try except and import the Python debugger, and then do a post-mortem. This is the way that you can make your program whenever it raises an uncaught exception to drop into the debugger so that you can actually see what's going on with it. The benefit of doing this over, say, dropping into the prompt, of course, is that when you drop into this, the debugger, the stack frame that caused the exception is still there. You see all of the levels of what was running at the time the exception was raised. So you can actually go back and look at each of those statements. You can pop and push. You can do things with those frames. And so it's a little more, not post-mortem, but like in this situation at the moment. So that's good. You may also have in your code where you simply want to drop into the debugger at some point, and you place those in your code right before you say you go into some suspect code. And that'll drop you into the debugger so you can actually see the call stack again. This one up here doesn't really show you the call stack per se. This drops you in the prompt, but it doesn't, it's not an easy way to get the call stack. The debugger here drops you into the call stack so you can say, yeah, sure, I reached this function, and I'm worried about it, but how did I get here? Who called me? Who called him? And so dropping into the debugger can be very, very useful for that. Taxonomy of bugs. So what kinds of bugs do we have in the world? We have the bugs that always happen. Those are the good bugs, actually, because you can find them. Then there's the bug that sometimes happens. And those can be a little frustrating, where you run it 3 times, it errors once. You're like, where is it happening here? What's going on? Then you have it where the bug only happens for someone else. Every time you ran it, it worked. And you gave it to somebody and it fails. And you're like, that code works, man. I know it does. And then there's one that only happens under load. You ran a little test case in your machine, and it worked under 3 records. It's ready, ship it. And then you find out that when the client loads up 10,000 records, it doesn't work. And so you have to deal with those kind of problems. And then there's the one that makes a module that takes too long. You run the program, and it never finishes, or it ran for an hour, and you're like, why did it should only take 5 minutes. What's it doing? You know, it shouldn't be doing that. So sort of got to track those kind of down. Make that bigger again. So if the problem always happens, of course, we can fall back to the print statement and put those in the code and try to figure out what's going on. And that's the most common when you're starting out or writing a new module or something. You may put that in there. Of course, putting in the good logging is preferable if you get the time to put that into your code or have the discipline to put it in as you're developing. And so that will point the finger immediately to usually what's going wrong with your code. Of course, if it always happens, single stepping is a good option. When it rarely happens, single stepping is frustrating. You know, it just means that you keep trying and trying and you're not hitting it, so it can be a problem. The bug that sometimes happens is, of course, you need to reconsider your design assumptions, because if it sometimes happens, maybe what you think is going on in the environment is not what really is going on in the environment. Especially the non-deterministic factors, ones that change, as in the chunking of packets or network traffic. Suddenly, depends on maybe at that instant there were a lot of network traffic going on, a burst of network traffic, and then it pauses and bursts and pauses. And so you have to think about, did you design for that? Did you handle that in your code? Maybe you didn't. Maybe you made assumptions about the environment. Of course, logging is good for the ones that sometimes happens, because if it happens 1 out of 10 times, that log. Problem, of course, if it happens 1 out of 1,000 times, 1 out of 10,000 times, is that you end up with very, very large log files, maybe, and you're wading through them, or you're filling up disk space with log files. And that can be very frustrating when it's a very rare bug. And so there's also what I call short-term logging, which is where you say start handling an operation, a request for a web or a database transaction. And so at the start of it, you open a log in some way in memory or on a temporary file, depending on the size. You log all the stuff along the way, and if you reach the end of the transaction or operation successfully, then you close and delete the log. And whenever that operation fails, you simply keep that log, and now you have a record of what went wrong during that part of the code. It won't help, of course, if a previous transaction somehow affected the code, broke the code or something, but it does help in the sense of, for the other kind of cases where the problem occurred within the transaction. And so that's a useful feature. The destination versus knowing the path. This is simply a little bit about people putting in unit tests will help you debug in the sense of point the finger at when you've introduced a problem. True, but it tells you that something went wrong, and therefore you can start looking for the bug. It doesn't always tell you, of course, what changed in your code. Suddenly, as I said, you're supposed to go from A to B, and you got from A to C. Okay, that's a problem. I got a bug, but if you use what are called logging tests, they can actually tell you what went wrong. Logging tests are like regression tests, is another word, I think, where when it's along the way, you're collecting and log details of the calculation that you're doing. My inputs were this. I calculated this along the way, and I printed the answer of this. And you keep that regression log in your test suite. And then when you run the test later, not only will it tell you that the output was different, but it will tell you that the code took a different way to get there. And then you can go look at that log and say, is that correct? Did I actually change the algorithm legitimately? Or is it taking a different route through the code because of something I've introduced into the environment? And then you can make a choice about that. It's also good for finding the bugs where the code did produce the correct answer, but not for the right reason. Sometimes you have functions that you've changed something in the function, and it's dropping out the bottom, taking the default case of returning none or false. And that was the correct answer, but it wasn't the correct logic. And now it's returning false in other cases as well, and you didn't know that. This kind of logging would tell you that I took a different route, I fell out the bottom, the code changed its behavior. So it's just, the output is not always sufficient. Then there's the bug that happens only to someone else. And those are especially frustrating when they're on the other side of the world. One place I was working, there was we developed a reporting program, and the developers ran it here in Dallas, and it worked fine. They gave it to production, and it worked fine here in Dallas. It's always running on the Dallas servers, and then they shipped it to a client on the other side of the world. But they were using it remotely. It was still running on the Dallas server, but it was being run elsewhere in the world by the marketing department. And it was printing incorrect report results. And it's like, why would it be different? It's running on the same machines, security privileges and everything. Turned out what it was that when the other part of the world was in such a place that whenever they ran it, marketing department ran it, it was running over the midnight of the Dallas server. And so now the reports are straddling 2 dates, and the reports are wrong. But it's very frustrating to have that kind of problem where you're like, it runs. Well, don't assume the time zone is one of the issues as well. So those are frustrating. So you reconsider your design assumptions. So differences in network between your site and the other person's site. More limited resources. And this permission, because like I said, the other site, the marketing department may not have the same privileges that you have. The current concurrency assumptions, like stealth apps. This is the one where you get the phone call and they're saying it's breaking, and you're saying, are you doing anything else? And they say no, and no, and and then you say, show me all the processes running on your machine, and you go like, oh, there's a couple of heavy-duty database things running in the background. And they're like, oh yeah, I forgot to tell you about those, and you're like, if you told me that, maybe I'd know that it affected my program. So you may not always assume, you assume that the program runs in isolation. It may run in a more social processing environment. And then software installation differences, where you've delivered the program and maybe your program is the same version, but maybe they have a different dependency loaded. And those can be frustrating. There's certainly tools in Python, build-outs, various other ways to track that. One of them I like is the -v option on Python. So if you run your program with -v or without any Python on it, it will actually print out the imports that are occurring as Python starts up, and as well as the imports performed by your program. And it shows you the full path name. So if you go poking through that, you can actually see that, oh yeah, sure, it imported this module, but it imported version 2.3 in this directory, which is not the one I gave them, or they should be using. And so it can quickly point the finger at something, or maybe something slipped in where you delivered all the dependencies but one, and it grabbed it from the system Python when it should have been included in the distribution, the release of the product. So -v is very good for that. -v also will show you all the deallocations when you exit Python, and that can also sometimes be useful for finding out things that didn't get garbage collected or large data structures and such. There's some interesting things you can do with that as well to say that memory didn't get reallocated early. Then there's the bug that occurs only under load. Whenever you get one of those, reconsider your assumptions based on anything about deallocation of things. So you may have a failure to collect garbage. So in a simple program, you run it. It generates lots of variables that are lying around in memory, but the program doesn't run for more than 5 seconds, over 20 records, say, and it exits. So you've never stressed the memory system. You've never actually filled up the memory system. But then you put it under a load system, and suddenly now you find out that you have all this extra garbage that's piling up, variables that you're not releasing, that you're not managing properly in your Python program. And so now you actually begin to see those problems. Another one is excessive nesting of stack frames, where that's a simple case, I said, of the recursion, where you ran it with 10 levels of stacks and it worked fine, but when you run it with 10,000 levels of stack because they gave it a bigger number or a more complex problem, now you find the difference. And so now that would be a case of it fails only under load. Delayed temporary file deletion. I've seen ones where they'll have like a work loop processing request, and they'll come back to the top of the loop when they're idle and say, I'll do house cleaning in my program. I'll delete temporary files or manage resources when I'm not doing anything else. Yeah, it works fine when you're not running under load. You put it under load, it never gets idle. There's so much work to do, it never gets back around to the housekeeping. And so that will introduce, of course, a problem. Exhaustion of threads or locks, where you spawn and spawn and spawn, and you divided the work up, and you can exhaust those. And so the changes in IO behavior of the load, because suddenly you're running around looking for the next packet, and in your case, the packet was there, but on the next packet, it's going to be there in half a second, and you didn't handle the wait properly. So that can be a problem. And of course, for under load, to make sure it doesn't happen again, make sure you use a realistic unit test. So if you use toy cases of unit test, then they won't find these kind of problems. So you want to make sure that you include some tests that are actually have used larger amounts of data or use more realistic parameters passed in. And then the bug that makes the program take too long. And beyond the use of the profiler, which of course you can run that up as a program that finishes. But sometimes you run the program and it's sitting there and you'd like to know what it's doing right now, rather than run the profiler, because if it never stops, the profiler's not going to give you very useful data. And so what you can do, back down. I hope that's not too small. You can actually set up a signal here, sig user 1, to an interrupt handler here that drops into the debugger. So you set that up in your main routine, and then you call your main. And before your main, you set it up in the top. OK, what that does is it hooks the control C, the interrupt your program call. So you run the program. It's sitting there running. It's been 5 minutes. You wonder what it's doing. You hit control C, drops you in the debugger. You print the stack and say, where is it in the code? And then you maybe poke around, or maybe you say continue, and you look at it again, and you break and look at it and break and look at it, and you can get an idea of, is it spinning forever in a certain loop, or is it jumping around the code doing useful work? And so that's a good way to get into the code. You may also have cases where slightly different, where you tie into the sig alarm, and here you can have a piece of code say that says this piece of code here should take no more than 30 seconds. You call the code, and then when you get done, you turn off the alarm. And then you could put those around your code under certain parts. And that way, it'll automatically pop you in the debugger, or you could, this debugger could be logging some event that says, hey, this code took longer than 30 seconds. You got a problem. So you can record your assumptions in the code this way. And so that brings up the questions or more, other war stories y'all might have about debugging. Things I thought about was maybe if anybody works on those areas, have they ever seen the perfect bug report, or maybe the worst bug report that you've ever seen, kind of a things. And the slides are available at this, by the way, this URL, so you can get the code samples. So I think we got a few more minutes. Yeah, barely. Any questions or any suggestions for tools or techniques that you've run into? I know there's some debuggers in here, so I know those people in here. It's their day job to debug stuff. So OK, well, that's all then. Oh.
Use something like Valgrind in Python?
Valgrind can be used for checking memory leaks, especially in C extensions. It's really good for that. Yeah. I haven't seen it used much for the Python code itself, but there is in the standard library a GC module, a garbage collection module, that will actually let you print out what's in memory at the moment, and printing that out and then later printing it out again and printing it out again and doing like a diff with some tools can actually show you where's the memory accumulating, who's not releasing this, who's a list that's building up, or stack frames that are not being released because you didn't clear the exception. Those kinds of things can be you can find them with the GC module.
I was looking for something to help with reference count
In C extensions. You have to get it perfect in C extensions, or you'll have something hanging around. Yeah, that's true. Yeah, send it back with the reference count of 0. Yeah, the GC will let you print out the reference counts. It'll actually tell you the number in the reference counts, and so that may help in some of those. If it didn't crash you first, of course, returning a dead object. But if you're still alive, you can print it out. Yeah, I've had to do that a few times in the ZOP framework. So. OK, well, we're on schedule, so that's all. Thank you.